In this video, we're talking about invariant points. Now, I've got a matrix given to me already. It's 2, -1, 1, 0, and I've got a coordinate here, 3, 1. And if I multiply these together, I get 5, 3, I believe. Let's just check that. Yeah, cool. Yeah, it is 5, 3. Fantastic. And I can move this coordinate around, put it somewhere else. And for this particular matrix, some of the points that I choose will result in nothing happening at all. So if I, for example, put it here, if I have the point 1, 1, the result I should end up with is also 1, 1. And let's just do the workings just to confirm that. So 2 times 1, 1 times, minus 1 times 1 is, yeah, it is 1. 1 times 1, 0 times 1, yeah, it is, cool. So for this particular point, this matrix has not changed it. So we could say that the point 1, 1 is invariant under that matrix. That matrix didn't do anything to that point this time. Here's a giant pink rectangle for me to write down the general formula for an invariant point. So if you have a matrix and you have a coordinate x, y, if the coordinate is invariant, then you just end up with exactly the same thing. So here's the general formula. Sorry if my screen's gone white. I had to make some space for my workings. So this is the setup anyway. I'm looking for the invariant points. I know that 1, 1 is invariant, but there might be some others. So what I'm going to do is I'm going to multiply out the left-hand side, and I'm going to see what I get from that. So I'm going to have 2 times x minus 1 times y, and then the vector on the left-hand side is going to look like this, 2x minus y. The bottom part of it is going to be 1 times x, 0 times y, so I'm just going to have x here. And then what we're going to do is we're just going to match things up, basically, so then I can just look at this bit here. That should match with that there. And similarly, the x and the y terms can match up. So it's kind of like a simultaneous equation, except we're going to have it looking like this. So not your normal looking simultaneous equations. In fact, this one is just x equals y. If you rearrange this expression, I'll just take the y over, and I'll take this x over. I'll have 2x minus x equals y. And notice this is going to give me exactly the same thing as well. I'm going to have x is y. So what this means is any point on the line x is y is invariant. Let's check that out. So here's my line y equals x, and here's the point 1, 1. As you can see, that is invariant. If I'm off the line, then my point is going to take me somewhere else. But if I'm on the line, no matter if my coordinate is 1, 1 or 2, 2 or 4, 4, or maybe some other numbers that I could find by zooming out, either way, we're going to have invariant points. Now, there will be situations where you don't have any invariant points. So let's take this matrix here. Let's attempt to find some. So if I simplify the left-hand side, I'll have 1 times x, 3 times y. And on the bottom, I'm going to have 2 times x, 0 times y. And I'm going to attempt to match terms up. So I'm going to look at the top terms. And I'm going to look at the bottom terms. And I'm going to get this. The top bit says x plus 3y equals x. And the other line says 2x equals y. Now I'll try and rearrange this. So I'll take the x over the other side, and I'll get the equation 3y equals x take away x, which is 0. And the second equation is just a straight line. It's the straight line y equals 2x. Now, the only solution to these together, and you might already have an inkling of where this is going. The problem is with this top equation, 3y equals 0, it forces the y value to be 0. And then, since we have this relationship y equals 2x, but we know y is 0, x must be 0 as well. So the coordinate 0, 0 is invariant. The origin is invariant, but nothing else should be. And let's just see that in practice. So here's the matrix, and doesn't seem to be invariant anywhere. Oops, just moved the whole screen. It is invariant here. So any matrix is invariant at the origin. Doesn't seem to be happening anywhere else. Cool.